Okay, good morning and welcome. I have to say it is a real pleasure to be back speaking to a live audience again. I've spent a lot of time over the last, 18 months or so, talking to my laptop. And now I actually get to talk to real people and, well, maybe I can actually see a few people as well as we're doing the presentation. So, what am I going to talk about? I am going to talk about the differences between ahead-of-time compilation and just-in-time compilation, and how that relates to performance of your application, and specifically when we're looking at microservice-based architectures. My name is Simon Ritter. I am the Deputy CTO at Azul. There we go. So the first thing to think about is, in terms of the JVM, what are the performance challenges that we face here? Because the JVM is very powerful. It's one of the primary reasons that Java as a platform has been so successful over the last 26 years and has maintained that level of popularity. But having a managed runtime environment does mean you get better performance in some respects, but it also poses some challenges in other respects. Now let's look at the things that we can think about there. So the first of those is latency. How quickly can we respond to a request from a client? And there are a couple of reasons why you get latency in the JVM, but the biggest one of these is down to garbage collection. Automated memory management, the JVM decides where to allocate space in the heap for your objects, and you as a developer don't need to worry about figuring out how to reclaim that space. It makes your life easier. The problem is that the way most algorithms work is that they need to pause your application threads in order to do the garbage collection work safely. So when they're marking objects that are still in use, they don't want you changing objects that you use, and when they're relocating objects in the heap, they don't want you changing data as well. Now, there are some other things that can introduce latency into a JVM, things like JIT compilation. If you start compiling code whilst the application is running, that can also interfere with the performance of your application response. So latency is a big one. Second thing is throughput. How can we look at the way that we get throughput for our application? How many transactions per second can we deal with? And a lot of this is dependent on how we can optimize the compiled code that we generate for a given method. There's a number of different techniques that we can use, and we'll kind of talk more about this as we go through in terms of what are called speculative optimisations and the effect that those can have in terms of de-optimizations and the reality of then degrading throughput as the application is being used. And really it comes down to the effectiveness of the compiled code. How heavily can we optimize that code as to how much throughput we can get for the given application? And then the last thing is availability. So how quickly can we start up an application, and how quickly can we deliver the optimum level of performance? This is very apparent with the JVM because we use bytecodes. It's a virtual machine, it's a virtual instruction set. So we use bytecodes, and those bytecodes get interpreted by the JVM initially, which is very slow. As we spot the methods that are being used more frequently, then we compile them using the C1 compiler, then we spot that they're being used even more frequently, we use profiling information we've collected, and then we recompile them with the C2 JIT compiler, and that gives us better performance. But that all takes time. And that's the warm-up time that we see associated with the JVM. So now let's look at the microservices world and how speed and performance impact on those. If we look at the changes that we've made by moving away from a monolithic architecture to a microservices architecture, this is a sort of diagram that kind of puts that into context. We have our users on the left, they're interacting with the system, and what we've decided to do is break it up into a number of individual services. Those services interact with one another, and they produce the results that the client wants. On the right-hand side, we've got some database type activity where we can maintain state and things like that. And one of the real benefits of using a microservices architecture, especially from a performance point of view, is that if we find that one of our services becomes a bottleneck in terms of performance, lots of different parts of the rest of the system are depending on that and using it heavily. If we only have one instance of it, then that clearly is going to be a situation where we're going to degrade the performance of the overall application. Now, if we were in a monolithic application, the only thing we could really do is to throw more resources at the whole monolithic approach. More memory, more processing, and so on. And that's very inefficient, because if it's only one part of the system that's the problem, then we may be wasting resources. In a microservice-based architecture, we have the ability to change that. So what we can do is we can say, okay, that particular service is being heavily used. Let's spin up some new instances of it, share the load across them using whatever techniques we need in terms of like Kubernetes or whatever to load balance across the different instances we have. And we can do that very dynamically. So we can spin up new instances when we need them. We can then shut them down when we don't need them. And in a cloud-based environment where we're in a very much a utility-based model, pricing's based on what we use, that is a very efficient way of dealing with changes in load. The other thing we need to think of when we're looking at microservice-based architecture is that our users are interacting with the whole system. Okay, well, that's obvious, yes. But what's the impact of that? The impact is that they interact with the system, they have a particular task that they're trying to achieve. And we need to look at the design of our microservices in terms of how many of those are being used. Because the more that we chain together, the more impact we can have on performance. And this is especially apparent when we're dealing with a JVM-based microservice. Because if we do introduce latency into our services because of garbage collection, for example, then the latency of the request to the user is a cumulative effect of all the different services that are being involved. So if each of those starts doing garbage collection sequentially, in effect, then we can end up with some very long periods of latency associated with our system. So it's something that we need to think about quite carefully when we design the system as to how that might impact. So let's look at the performance challenges in terms of microservices related to what we spoke about earlier from the JVM perspective. So the first is this ability to spin up new instances. And we need to think about how quickly we can do that. Are we going to need to provision a new cloud instance? That could be something that could really take a long time. Or are we going to cache a number of instances and then make those available so that we can start up the individual services from that? Once we do that, how long is it going to take to reach the full transaction processing speed that we need for that service? Again, if we're going to go through a warm-up phase associated with the JVM, then we're not going to be able to deliver high performance, high throughput immediately once we've got that service started up. So spinning up a new instance is going to take longer in terms of its effectiveness, and we may need to think about spinning up more instances or creating other approaches to that. That becomes especially relevant when we're talking about serverless computing, where we're doing sort of a function that's only going to be used for a very short space of time. Second thing is obviously throughput. And from a microservice performance perspective, what we need to think about is how many transactions can we process with a given service. The more that we can get through one service, the less instances of that service that we're going to need to provide to handle the load from our users. And the third thing, again, coming back to what we said earlier, is latency. And that could be in the extreme form if we get something that goes into garbage collection and has a long pause associated with that. That may even trigger the overall architecture to think that that service has gone offline and therefore have to restart it or to create new instances to deal with the fact that that has, in effect, disappeared. So there's a number of things that we need to consider quite carefully with that. Let's talk a bit more about AOT and JIT then, and what are the different approaches to compiling our code. So if we look at Java specifically, we can take the approach and say, let's compile our code ahead of time. That solves a lot of the problems that we might see in terms of that warm-up, in terms of that startup time associated with the service. And this seems to be quite a sort of common approach to thinking about how to deal with Java-based microservices at the moment. So what you do is, rather than taking your source code and compiling into bytecodes, you compile straight away into native instructions, and that way you can run them immediately on the platform that you have, and you don't go through the whole warm-up effect. But that's not necessarily the best approach, because there are some things that you need to think about quite carefully. First of those is that, yes, we can compile, let's say, for an Intel architecture with a Linux operating system. But not all Intel processors are the same. Clearly, they can have different chips, different clock speeds, but they can also have different microarchitectures in terms of the instructions that they actually support, depending on how modern they are. And so you have to think, do we compile our code based on a knowledge of exactly which platform we're going to run on and which processor we're going to use? Or do we compile based on the fact that we might have slightly older chips or we might have slightly newer chips, in which case we can't take advantage of some of the more modern features? A good example of that is vector operations. And there are 3 different variations of this: as AVX, AVX2, and AVX512. And that determines how big the register is that you're going to use for your single instruction multiple data approach. So do you compile based on 128-bit wide registers, or do you compile on a 512? Well, you know, that's the kind of thing that you have to think about. The other thing that you lose when you do this is the whole write once, run anywhere approach that you get with Java. So you can't just move it to a different machine that maybe is running Windows. You'd have to recompile. Okay, probably not too much of an issue. But the other thing, which is more significant, is the fact that you're doing static analysis of the code paths that are being used. That means that you've got no visibility of what's actually going to happen at runtime. So you're saying, okay, let's compile the code based on what we can see there and just knowing what the code actually does statically. The other thing that's quite important is the fact that Java is a statically typed language, but it is dynamic in the point of view of class loading. You can load classes at runtime. It's very common to do that. And that will have an impact on how effectively you can optimize the code you generate statically. One of the most common techniques for improving performance is method inlining. You take your method, and rather than creating a stack frame, running the method, then popping the stack frame off, you just say, well, let's take the instructions of that method, put them into the loop, and avoid the repeated stack frame creation and popping. You can't necessarily do that if you don't know which method is going to be called. So if you are running with dynamic class loading, maybe at runtime you change the method that actually ends up getting called, and that way you can't inline it when you do ahead-of-time compilation. There are definitely techniques that can alleviate that. You can use profile-guided optimization. That's something that's been around for a long time, where you run your application, having compiled it statically, you run it, you get some profiling information, feed that back into the compiler, and recompile it again, knowing how it works when you run it. But that's still only taking a particular run as the reference implementer or the reference data. If you've got something which changes a lot, then you're still going to lose out in terms of the performance that you can get from that. So the optimization opportunities are definitely reduced. You've got less method inlining, and again, speculative optimizations, you can't use those in the same way that you can with different approaches. And also, the other thing you've got to think about when you're doing ahead-of-time compilation with Java specifically is that because there is this idea of automated memory management, how does that happen? How does it actually happen at runtime if you're compiling statically your code? Where does the allocation happen? Where does the garbage collection happen? We can also think, obviously, about the opposite approach, is what we use most of the time, which is just-in-time compilation. So now what we're doing is we're saying, find the methods that are being used most frequently, and then compile them as the application is running. What that does is it allows you to see a full set of information about how that application is being used. So you've got profiling information of the running application, and you can use that to optimize to the best possible way. The other thing you've got is a very accurate view of all the classes that are currently loaded, meaning that if you do want to do method inlining, you know exactly which method is going to be called because you know which class is loaded, and therefore you can use more aggressive inlining to improve the optimizations. And you can use speculative optimizations. However, the downside of that is that you have to do a lot of work whilst the application is running as well. That takes away from the resources you've got in terms of the CPUs, the cores, and even the memory, because you're doing this compilation at the same time, concurrently with the application. And that's going to reduce the throughput. It's also going to introduce latency by having stop-the-world pauses as you do method compilation as the application is running. Talk a little bit more about speculative optimizations, because these are very important to the ability to use JIT compilation. Here I've got a method which is a slightly contrived method, but it does demonstrate what we can do in terms of improving efficiency of code. So my method is called compute magnitude, and what it does is it takes a value, and then it says if the value is greater than 9, we're going to determine a bias that we want to use by calling another method that does some sort of computation. If the value is not greater than 9, then we just set the bias to be 1. And then we return the log base 10 of the bias value plus 99. Great. Now, if we profile that and we let the application run, we may find that in the run of the application, we've never had a value that's been greater than 9. When we come to compile the method, what we can do is we can make some changes to the code which will improve its efficiency quite markedly. What we do is we say, okay, well, if we know that up until now, we haven't had a value that's greater than 9, let's assume that that will happen in the future as well, and we'll continue to not have a value greater than 9. In which case, we know the bias is always going to be 1, we know 1 plus 99 is 100, and log base 10 of 100 is 2. So let's avoid all that work and just return 2 every time. Now, clearly, we have to have a situation handled where we do have a value that's greater than 9. If that happens, we then jump to this method called uncommon trap, and what that does is it says, ooh, we made a mistake, let's throw away the code that we compiled and then recompile it based on the fact that we need to handle both branches of that if statement. So this is where we get a de-optimization, and de-optimizations are what we really don't want to happen because obviously we're throwing away code and then having to recompile. Now, what we found at Azul in terms of analyzing code is that over half of the performance benefits we get through JIT compilation are down to these speculative optimizations. It's not just about complicated situations like that. Even simpler things like null checks can be eliminated a lot in terms of speculative optimizations. And so this really is critical for getting the best performance from your application. And also, the obvious thing is that if you minimize the number of de-optimizations, you're going to improve the way that your code is going to work. So what are the different approaches that we can take in terms of solving this startup speed problem? If we want to have less warm-up time and get to a faster level of performance as quickly as possible. Well, one of the sort of common things that people are using at the moment is Graal VM. So just a show of hands, anybody tried Graal VM? Oh, yeah, so that's probably a good, maybe 40, 50% of the audience. So Graal VM is one of those things that's been around for quite a long time. I used to work for Sun Microsystems back in the day, and Graal came from Sun Labs. And it's actually a series of projects that were started there. And Oracle have kind of bundled it all together and overloaded the term Graal to confuse people. Now, I don't think they really did that, but it is a bit confusing because the Graal VM represents several different things, which includes the Graal JIT compiler. Okay. One of the big things about Graal is it is designed to be polyglot and run lots of different languages, not just JVM-based languages, Scala, Kotlin, Clojure, and so on. What you can do is you can run all sorts of different languages, and as you can see from the diagram here, there are different pieces involved. So if we look at the Java side, that's quite simple, because what you do is you take your Java code, and then rather than running it through the C2 JIT compiler, you can run it through the Graal JIT compiler, which is actually written in Java. And then you can use the JVM compiler interface, and you can either run it through Hotspot as the JVM, so you're just running it as code through there, or if you want to create a native image, you can compile it directly into native instructions, and you use the substrate VM to provide the functionality that you need to do things like garbage collection and thread synchronization and so on. Now, for other languages, non-JVM specific ones, like Ruby, like JavaScript, the scripting type languages, then you need the Truffle framework. And that's a language implementation framework, produces or uses abstract syntax notation, which can then be fed into the Graal compiler to generate code to run your application. For more traditional compiled languages like C and C++, they also use another layer, which is called Sulong, and that's based on LLVM, which is a compiler project that generates intermediate representation for that, passes it to Truffle, then compiles it using the Graal compiler. So there's a lot of different options with Graal in terms of how you can use different languages and have them run on top of the different parts of the system. Again, Graal uses profile-guided optimization if you've got the Enterprise Edition to try and optimize things when it generates static images. So if you look at Graal VM for Java applications, you can essentially do it two ways. You can either run it as a traditional JVM type application where you're using bytecodes, running them through the Graal JIT compiler rather than C2, and use Hotspot. Or you can use native images, which is what a lot of people do to really get fast startup and small footprint for their microservices. And what you're doing there is, as I say, creating AOT compiled code. It is fast startup. Oracle claims up to 50 times faster than using the JVM, and low memory footprint, again, Oracle claims 5 times smaller than you would get if you were using a JVM. It does use, as I said, the substrate VM to handle the managed runtime part of the functionality, and so memory management has to be done somehow. It is something to think about because the way that it does garbage collection is quite similar to G1 in that it uses a region-based allocation, but it's a sort of hybrid approach with region-based allocation and some static analysis as well. So it may introduce longer pauses than if you're using a concurrent garbage collector. There's another project in OpenJDK that was proposed in April 2020. And this was really looking at doing a very similar thing purely for Java. So creating native images for an application so that you didn't have to go through the JVM and you didn't have the overhead of various things there. It is designed, as they describe it, as a closed world. So it limits some of the things that you could have done if you're running on top of a JVM. There's no dynamic class loading at runtime, and there's also no dynamic bytecode generation at runtime. I'm kind of confused with this one because they proposed this project in April 2020, and to date, nothing has been done. There is no mailing list, there is no clone of the repo. They announced it and then did nothing. So, a bit confused why they bothered doing that. Another approach is what we have done at Azul. And we have a different JVM to Hotspot, which we call Prime. And part of that is a technology called ReadyNow. So what we do in terms of our JVM is to try and improve performance. So we look at the limitations that I talked about at the very beginning of the presentation. And we said, OK, well, rather than writing a JVM completely from scratch, let's take Hotspot, because a lot of the code is very good, but there's certain things we can improve on. And having made those changes, we need it to be a drop-in replacement for other JVMs. So we run the TCK tests, and we make sure that it passes all of those, so it's functionally equivalent to Hotspot. There's no differences in terms of how it will run your bytecodes other than from a performance perspective. So what we do here is it's all about low latency, high performance. And to do that, one of the things we do is remove all of the garbage collectors in Hotspot and replace them with one called C4, which is a truly pauseless collector because it does everything concurrently with your application threads. The other thing we've done more recently is to replace the Falcon JIT compiler in the same way that Graal does, but rather than using the Graal JIT compiler, we use one based on LLVM, the compiler project. And that allows us to get some good performance improvements that way. And then, as I said, we've got this ReadyNow and compile stashing technologies, which is designed to reduce warm-up time. What does ReadyNow do? Well, the idea is that if you run your application, you go through the warm-up, you compile your methods, you recompile your methods, you de-optimize, you re-optimize, eventually you get to a steady state where you've got all the methods you need regularly compiled and optimized. Great. When you restart your application, you have to go through the whole process again. So what we do is we say, run your application until you're happy with the level of performance, and then we'll take a profile. And the profile consists of 4 things. All the classes that are currently loaded, all the classes that are currently initialized, because that could actually be a subset of loaded classes. We also record all of the profiling data that was collected during the interpreted mode and also the C1 compiled code mode. And most importantly, any speculative optimizations which we used, and then we had to de-optimize and throw away the code, because clearly we don't want to make the same mistake again. The great thing about this is there's no restriction about when you take the profile. You can let the code warm up for as long as you like. So whether it's 2 minutes, 2 hours, 2 weeks, doesn't matter. Just let it get to the point where you're happy with the performance and then take your profile. The other thing you can do is you can take profiles for different workloads. And by that I mean you could have a profile that you collect on Monday morning, you could have a profile you collect on Friday afternoon. If you need to restart your application, depending on when you restart it, you can use the right profile to address the load that you would expect to have at that time. What this allows us to do is to say, when we restart the application, rather than going through that whole process again, let's use the information in this profile. Let's immediately load all of the classes that we can, initialize all the classes we can from that list, and then compile all the methods we know we're going to need using the profiling information we've collected and the de-optimizations so we know what we don't want to do with speculative optimizations, and do all of that before you get to the point where you're starting your application in main. That way, when you get to the main entry point, you're going to have about 98% of the performance that you had when you took the profile. And you start your application, and off you go with very, very high level of performance. Run about 2 or 3 transactions through that, and you'll get to that 100% level of performance. Now, we can't quite get to 100% straight away, and there's a couple of reasons for that. One is that the way that the JVM is specified, there's certain things you have to do in a particular sequence when you start it up, and that limits some of the things that we would need to do with our profile. And the other thing that we have had some issues with in terms of the way that we can compile code is around some of the things like lambda expressions, because lambda expressions rely on invoked dynamic, and so you defer the implementation of the lambda expression to runtime, and so those are a little bit more complicated in terms of how you generate the code for those. We are working on some solutions especially to the lambda expressions at the moment. So the effect of this, if we look at latency specifically, is that if you take your normal application, you run it without ReadyNow, you're going to see something like this blue graph, where you start off quite slow, latency because you're interpreting bytecodes, so the ability to respond is slower. And then as we compile methods, we'll gradually see that latency decrease because the methods are now being compiled into native instructions. And we'll see up and down in the graph because we're getting the optimizations at the same time. We can then do different generations of profile, and we can see different effects, and we can gradually bring that down closer and closer to the fact that we've got sort of 0 latency associated with the compilation of code dynamically during runtime. The thing is, though, if we look at a simplified version of our performance graph, so this is now not latency, this is performance. If we look at a simplified graph of without ReadyNow, start off slow, gradually warm up, get to our optimum level of performance. Okay. If we look at it with ReadyNow, it looks like this. So now we've got a much steeper graph, so we're getting to our optimum level of performance really quickly. That's really good. Except we've got this kind of blank bit before the application does anything. And that might be bad, because what's happening there is obviously we have to do all this work first. We have to compile the code, we have to class load, initialize, and so on. So we thought, how can we get around that? How can we reduce that as much as possible? And we looked at the way that the compiler worked, and we said, okay, what's happening is we're taking our bytecodes, and because we're using our Falcon JIT compiler that's based on LLVM, what we essentially do is convert the bytecodes into LLVM intermediate representation, pass that into the compiler. The compiler then needs to know how to optimize that method. And to do that, it will ask certain questions of the virtual machine using callbacks. And this is essentially asking it about the profiling information that's being collected whilst that method has been run. The VM is then going to provide some responses to that, which is the input to LLVM to understand how to optimize its code. It will then use that, generate some machine code, and we get a compiled method. Okay. Now, the other thing that we know about LLVM is it is a fully deterministic compiler. And that means that if we take the same inputs, we're guaranteed to get the same output. If we look at a method that we have in Java, we're going to see, in terms of the data that we have, something like this. So our method is going to consist of some initial intermediate representation generated from the bytecodes. We're going to have a live profile associated with that method. And then there'll be a set of queries and responses that LLVM uses to optimize, and then the machine code that's generated. Which means that if we have identical inputs, if we haven't recompiled the method, and we're using the same profiling information as we had before, that will result in the same queries and responses. That means that we're guaranteed that the compiled code that's generated by Falcon is going to always be the same. Right, we can take advantage of that. So what we now do, in addition to taking the profile, which consists of classes loaded, classes initialized, profiling data, and de-optimizations, we also take a copy of all the code that was compiled from the run of the application. That way, we can put our compile stash, as we call it, effectively as a cache between the JVM and the compiler. If we pass in the intermediate representation and we know that the profile hasn't changed, we get a match on the method that we need to compile. Rather than getting the compiler to compile it, we simply say, take the code that we've already got, pass it back, and avoid all of that workload. What that then allows us to do is take that graph where we've got this sort of blank period where the application doesn't do anything and shrink that down. So now what we can do is reduce the amount of compile time that's required by up to 80%, and the CPU load before the application gets to doing its work by up to 60%. So that's a good improvement in terms of what we can do there. The other thing that I want to talk about is Java on CRac. Now, I've got to say that our marketing team may have to rethink the naming of this, because it might not be the best. But this is an interesting research project that we're doing at the moment. Java on CRac. CRac stands for Co-ordinated Restore at Checkpoint. And as I say, it's a research project that we've started to look at pausing and resuming JVM applications. And we've now got this as an OpenJDK project. So if you go to the OpenJDK, you'll find CRac as a project there, and you can look at what we've been doing. What we did was we looked at some other technology that's already been around for a while, which is CRIU, Checkpoint Restore in User Space for Linux applications. And I'm sure some of you have come across this in other places. And that was originally targeted at live container migration. So you could take copies of containers and migrate them to other machines as they were running, in effect. Now, if you think about taking a running application in Java and simply freezing it, taking a snapshot of everything, the code that you've got, the registers and everything, and then being able to restart it at some point later, that's very difficult. And you can't just take a snapshot and then restart it. Things like file descriptors, things like network connections are just not going to work if you do something like that. So the key thing about coordinated restore at checkpoint is coordinated. What we do there is we are creating an API which says if the application is running and it decides that you want to take a checkpoint, you can let the application know, and then it's up to the application to take whatever steps are necessary to make itself ready for a checkpoint. And that involves things like closing files, closing network connections, and tidying up things which it will need to restart when you use the restore part of the functionality. And the thing is that, you can actually enforce rules with this so that if the application hasn't done enough work, then it won't actually take a snapshot. What then happens is, clearly, you can restart the application at a point later in time using the snapshot. And again, the API is used to say, right, I know I've been restarted. Now I can open the files I need. I can reconnect to network resources I need and coordinate the restart of the application. This can lead to some very impressive results. So if you look at our GitHub repo, github.com/CRac, we have created a proof of concept of this, and we've done some comparisons between just running standard OpenJDK and then OpenJDK on CRac. Spring Boot. If you take a Spring Boot application like we did and you run it to the point where you get your first operation in terms of application functionality, in the machine in the example that we ran here, it took nearly 4 seconds to go from cold to processing a transaction. Using our checkpoint restore, coordinate restore at checkpoint, that reduced to 38 milliseconds. So that's 2 orders of magnitude faster. And remember that you're also going to get the same level of performance in terms of JIT compiled code with all the speculative optimizations, with all the ability to do aggressive method inlining and things like that. So very, very fast startup with the optimized code and better performance. We did some other benchmarks here. You can see Micronaut, that took a second to get up to speed, 46 milliseconds using CRac. Quarkus was 980 milliseconds. So, Quarkus is one of these frameworks that's designed for very fast startup. Great, so that was 980 milliseconds. Using CRac, we got that down to 33 milliseconds. And XML transform, which is probably not the best benchmark to look at, that was 4.3 seconds to processing a transaction, and we reduced that to 53 milliseconds. So again, you can see that there's some really quite impressive results that we're getting with this. It is still only a research project. I wouldn't say this is quite ready yet for production, but it's got some interesting ideas, I think. Just to summarize then, basically faster startup or faster code. I think it's obvious that microservices can benefit from fast startup. If you want to have this dynamic ability to spin up services, then that can really benefit from having the ability to go straight to 100% level of performance. But it isn't always necessarily essential. If you've got a longer running microservice that's going to run for minutes or hours or longer, then you might need to think, is it really important for me to start that service up super, super fast, or am I more interested in getting better overall performance once it's warmed up and once it's doing what it needs to do? Overall performance, like I say, can be just as important. Consider all the aspects of the application performance, so startup time, throughput, and latency. And if you're interested in trying our Prime JVM, as I say, it's got different garbage collection, it's got different JIT compilation, it's got ReadyNow. You can go to our website here, azul.com, products Prime stream download, and you can try it for free. And with that, I think that is the end of my presentation. And I would just make one more plug for one of my colleagues, Hirchen, who I can't see where Hirchen is. Where are you here, Hirchen? You said you were going to be here. Up at the back there somewhere. I can hear a voice. Okay, so Hirchen works for Azul as well, and he's responsible for Fujay.io. And Fujay is Friends of OpenJDK. And it's a website that we've started to provide lots of information about OpenJDK, if you're interested in seeing the differences between different releases in terms of command line flags, in terms of the updates and what's been included in the updates from security perspective, from a bug fix perspective, there's all sorts of information there. It's very, very useful. There's lots of blogs on there as well. It is not an Azul site. It's a vendor-neutral site. We've got lots of partners that help us with that, people like SNCC, Pyara, JFrog. There's lots of other companies involved in this, so I would strongly recommend you to check out fujay.io. And with that, thank you very much.